Welcome to this third lecture in this week. We are going to today see the concept of stability. It is a very, very important concept in control theory, and actually when you look at control theory books, almost maybe half of the books would be related to the concept of stability. So it is a very, very important concept, and it is what we usually make sure before we establish any performance criteria on the system. So before setting the settling time, or before before adjusting the rise time, maximum overshoot, etc., we make sure that the system or the closed loop system is actually stable. And once we establish that, once we make sure that the closed loop system is stable, then we can adjust other performance measures on the system. So sometimes feedback would make a stable system unstable. So sometimes the feedback loop that we established in the systems can make the system unstable. So even though the open loop system behaves quite fine, when we close the feedback loop, sometimes the closed loop system can be unstable. So, and this actually tells us that we have to be very careful when we try to establish or we try to put up some feedback loops. So an unstable system is actually useless. So either something breaks in the system when it's unstable, or it would work really, really bad compared to stable systems. Therefore, feedback when it should be done correctly, when it is actually done. So an incorrect feedback might sometimes make things even worse than without feedback. So today's topics, as I said, is stability. And I'm going to start with the definition of stability that we are going to use in this course. And this is going to appear over and over towards the end of the course. So you will encounter, or you will try to make sure that the closed loop system is stable over and over in this course, in the coming topics. So therefore, it is very important that you understand this definition. So we consider a system. This is usually the closed loop transfer function of the system. G closed loop of S is equal to, let us say, N of S over D of S. This D of S, we call it as the characteristic polynomial of the system. And we know that the poles of the closed loop system are determined by the roots of D of S. So when we write D of S equals to 0, this is called the characteristic equation. Okay? And the solution of the characteristic equation are the closed loop poles. Okay? Solutions of the characteristic equation are the closed loop poles. All right? And the stability of a system is determined by the location of the closed loop poles. If the closed loop poles satisfy some important criteria, then we say that the closed loop system is stable, and then we can try to adjust other performance measures on the system. So let us make the definition of stability. A system, and in general, we are actually meaning the closed loop system in this case, is stable if and only if all closed loop poles which means they are the roots of D of S, roots of the characteristic polynomial, lie in the open left half plane. And by the plane here we mean the S plane, okay, the complex plane. So, and all poles lying in the open left half plane means that all poles satisfies this inequality. Real of S. S is any pole of the system. Real of S should be strictly less than 0. I'm going to show the same thing using pictorially on the S-plane, but before that I will write what this stability concept is called. So this stability concept is called bounded input, bounded output, stability. A short name we give to this stability concept is BBOS stability. Okay? So now let us try to go over this definition to explain it more. So we call the roots of D of S, the roots of the characteristic polynomial, or the solutions of the characteristic equation, as the closed loop poles. And we call a system a stable system. We call a closed loop system a stable system if and only if all closed loop poles, roots of this D of S, they lie in the open left half plane. So what do we mean by that? We mean the following. So this is my complex plane. And this is the imaginary axis, okay? I don't include the imaginary axis here because we are told that the roots should lie, or poles should lie, in the open left half plane, meaning that I won't include the boundary here, which is the imaginary axis. So this is my open left half plane. Okay? And the condition for that, we have already written that, is a real of S is strictly smaller than 0. So this open left half plane means that all poles should have real parts strictly less than 0. So there shouldn't be any poles with real parts equal to 0 or strictly larger than 0. All right? And we call this stability concept, when a system satisfies this stability concept, we call the system stable, or sometimes we use the adjective BBOS stable. Okay, so if a system has closed loop poles given like this, then it is stable because all poles have real parts strictly less than or equal to less than 0. So this is a stable system. I might have, of course, the real poles as well. I can have the unstable systems, which might have pole locations given like this. This is an unstable system. Why is that? Because there are some poles of the system which are on the imaginary axis, which have real part of S equal to 0, which doesn't satisfy the stability criterion. And I might have, of course, an unstable system which have a pole in the right half plane. Okay? As soon as we have a single pole or a single or more poles in the right half plane or on the imaginary axis, that system would be called unstable. And this stability concept in the control literature is called BBOS stability. Okay? It is the bounded input, bounded output stability, which means that a stable system, if we have a stable system whose poles are all in the open left half plane, that system gives always bounded outputs to any bounded input. Okay? Stable systems give bounded outputs to all bounded inputs. This is the meaning of BBOS stability. Of course, I need to talk about what boundedness means in this case? Boundedness means that the function, the time function that we are considering can be actually upper bounded by a constant. Okay? So I can actually write the function f of t is bounded if we can find an upper bound capital F, which is a real number, such that f of t is, so let me say, absolute value of f of t is less than or equal to f for all t in R. Okay? So this is our boundedness concept. A time function is called bounded if we can find a upper bound, capital F, which is independent of time now, such that this function, the absolute value of it, is smaller than or equal to that upper bound for all time instance f. All right? For all time instance t here. All right? So we need to have this inequality satisfied for all time instances, and we need to be able to find an upper bound f such that this f of t, absolute value of it, is smaller than or equal to that upper bound for all time instance. So what type of functions are bounded? So here, so is this function a bounded function? Yes, if it behaves like this for all time instance, then I can find an f. Okay, so this is going to be my f here, and I can see that if I take the absolute value of this function, then the absolute value will always be smaller than or equal to f for all time instance. That means that this function is actually bounded. So here, let us look at some example signals. For example, the unit step function. That is the unit step function. Let us say that this is the unit step. Is this function bounded? So we see that the intuitive meaning of boundedness is that it's not diverging. Okay? So we see here that the unit step function is actually bounded. Why is that? Let me call this u of t. Okay? I know that u of t is absolute value of it. It really doesn't matter when I take the absolute value here, because the function is either 0 or positive. So this is smaller than or equal to an upper bound u. What can I choose as my upper bound here? I can choose u equals to 1, for example. Then this inequality is satisfied for all t. Or I can choose any number, any real number which is larger than 1. For example, 1.5 would also do. All right? So I can find infinitely many upper bounds for this function. Therefore, the unit step function is a bounded function. What about the sine function? So let us say that this is 2 sine t. Okay? So that this maximum point, let us say that it is equal to 2. Okay, and this minimum point is at minus 2. So this is the function 2 sine t. Is this function a bounded function? T, let me call this function as my f of t. Okay? If it is a bounded function, then I need to be able to find an upper bound for this function such that this type of inequality is satisfied for all t. And it really looks quite easy in this case. So we see that f of t is smaller than or equal to 2 in this case, and that becomes my upper bound here, f. And this is true for all t. And here, similarly, I can choose any number, which is any real number which is larger than 2 as my upper bound, and I can show that this function is a bounded function. Now let me look at another function, the unit ramp function. All right? This is the function t. Let us say that this is r of t. for t larger than or equal to 0. Is this function a bounded function? Meaning that, can you find an upper bound, R, capital R, for this function, such that the absolute value of this function is always smaller than or equal to that upper bound for all t? Your answer needs to be here, no, because whatever bound I choose here, I can choose the bound 1, for example. I see that for some time instance, this ramp function gets above the value 1. Okay? Or I can choose the candidate upper bound 2. I see that again for some time instance that this function goes above the value 2. So whatever real number I choose here, this function is going to go above that real number. So that in this case I really cannot find any upper bound for this function which would satisfy such an inequality. Alright? For all time instance. That means that this function is an unbounded function. This is not bounded, or let us say unbounded. Okay? And these two are bounded functions. So what did we say about stability? So a stable system would always give a bounded output to a bounded input. All right? So you can give the system any bounded input and you would know that if that system is stable, the output is going to be a bounded function. Okay? Then what does it mean to be an unstable system? So an unstable system means that there exists a bounded function, which is the input of that system, which would result in an unbounded output from that system. So in practice, we always give our system some bounded inputs, and really we don't like the output to grow unboundedly. All right? So that is why we would actually ensure that all of the systems that we work with are actually stable systems. An unstable system can sometimes give unbounded outputs to some bounded inputs. And that is a problem for us because in that case, while working with the system in practice, I can actually give the system some bounded input and the result can be unbounded. Some things can explode in the system or some things can get broken. All right? So that is why we don't like unstable systems. So now let us try to understand why the criteria for a stable system is this one. Okay? If all the poles of the system lie in the open left-half plane, then we are sure that actually that system is a BIBO stable system. Okay? Why is that? For example, why can't we include the imaginary axis here? All right? Let us ask that question. So in our investigation of Laplace transform, we have seen that poles in the left half plane would give us decaying exponentials. Okay? Poles in the right half plane would give us growing exponentials. All right? And poles on the imaginary axis would give us some constants or non-decaying or non-growing oscillations. And the reason for this criterion is just those facts. So for example, for a stable system, why can't we include the imaginary axis, a pole on the imaginary axis? Okay? So suppose that I have a system which has a pole on the imaginary axis at the origin. Okay? origin is included on the imaginary axis, and it's the only real point on the imaginary axis. And suppose that I have this system. So suppose that I have a closed loop system which has a pole exactly at the origin. Then I'm going to ask you the question, is this system stable? Is this system BIBO stable? Okay? Your answer should be related to this criterion. What is the criterion for BIBO stability? All poles of the system should lie in the open left half plane. So no imaginary axis pole, no right half plane pole. All poles should be in the open left half plane. All right? And according to that definition or that criterion, this system is not BIBO stable. Okay? Because it doesn't satisfy the real of S strictly smaller than 0 criterion. I have a pole which would satisfy real of S exactly equal to 0. Okay? So this means that this system is not BIBO stable. What does it mean? This system does not give bounded outputs for all bounded inputs. This system does not give bounded outputs for all bounded inputs. That means that I can find at least one bounded input to this system such that the output is unbounded. Okay? The system is not BIBO stable, which means that this system does not give bounded output to all bounded inputs. That means that I can at least find a single bounded input such that the system would give an unbounded output to that bounded input. Okay? So what can be that bounded input that I can give to this system? So here I'm just going to consider the unit step function. Let us give this unit step function to that system. Consider the unit step input. So I have u of t is equal to 1 for t larger than or equal to 0, and u of s is equal to 1 over s. And I know that this input is a bounded input to this system. Okay? Because this input is a bounded function. So let us calculate the output of this system to that bounded input. Okay? So the y of s, so I'm calculating the step response of this system. All right? It is g closed loop of s times the input Laplace transform, and this is 1 over s, and this is 1 over s, and this gives me 1 over s squared. So the output of the system to unit step input is in Laplace domain 1 over s squared. So what is the output of this system then in time domain? It is going to be the inverse Laplace transformation of 1 over s squared, which we know as the unit ramp function for t larger than or equal to 0. Okay? And we know that by this argument here that we made, we know that this is an unbounded function. So this is a bounded input, and I have get an unbounded output. To that bounded input. Okay, that means that this system really cannot be a BIBO stable system. But we have already determined that by looking at the pole of that system, because it has a pole exactly on the imaginary axis, which is not included in our stability criterion. Okay. So this was one of the examples that I would like to show you. The second one is going to be the following. What happens if a system has poles exactly on the imaginary axis, but double poles like this? Complex poles on the imaginary axis. And I know that such a system, what can be the transfer function of that system? let us say that this is j and this is minus j, then my transfer function can be, for example, 1 over s squared plus 1. Okay? So is this system a bibostable system? According to the definition of the stability, it is not. Because it has poles exactly on the imaginary axis which are not included in the open left half plane. That means that this system is Bibo unstable. That means that for at least a single bounded input, this system will give an unbounded output. Okay? There exists a bounded input for this system that would make the system give an unbounded output. What can be that bounded input in this case? So I will just consider the following input Laplace transform. U of s is equal to 1 over s squared plus 1. So the same input type, input Laplace transform, as the transfer function of the system. So what is this input in time domain, u of t? What is the inverse Laplace transformation of this? If you remember the sine and cosine function, you can remember that this is the Laplace transformation of sine t, okay, for t larger than or equal to 0. Is this bounded? Is this input a bounded input? Yes, it is a bounded input. So what would be the output of this system to this bounded input? I'm just going to multiply the transfer function with the input Laplace transformation, and I would get y of s is equal to g closed loop of s times u of s, and it's going to be the multiplication of these two, s squared plus 1 square. Okay? And then I can ask you, what is the inverse Laplace transformation of such a Laplace transform? So you need to remember the inverse Laplace transformation properties, or Laplace transformation properties here. When we have double poles exactly at the same location, here and here, you need to remember that there is going to be a t multiplication on top of this sine t and cosine t. So I would have here, y of t would be looking like as follows. A times t cosine t plus b times t sine t plus c times cosine t plus d times sine t. Of course, these a, b, c, d are going to be determined in your inverse Laplace transformation. Just try to take the inverse Laplace transformation of that function, and it's going to be in this form for some a, b, c, d. Okay? And these terms, t times cosine t and t times sine t, they are actually unbounded terms, unfortunately. So when you have the amplitude of sine or cosine growing in magnitude, such a function would be an unbounded function. Unbounded output. Okay? So you see that there exists a bounded input for such a system transfer function, which would make the system give an unbounded output. Okay? So here, what would have happened if I actually gave the system a sinusoid at another frequency? For example, u of t is equal to sine 2t. Okay? If let us try to look at that. So we have found for this unstable system, we have found an unbounded output which is actually triggered by a bounded input. All right? So what would happen if I give this system an input sinusoid at the other frequency, sine 2t? Okay? U of t is equal to, let us say, sine 2t. This is also a bounded input, okay? But do you think it is going to cause an unbounded output at the output of the system? Let us look at it. So I have u of s is equal to, I would have 2 over s squared plus 4. And what about the output Laplace transformation? It is g closed loop of s times u of s. Okay? It is going to be 1 over s squared plus 1 and 2 over s squared plus 4. All right? And I need to now take the inverse Laplace transformation of this Laplace transform here. For that, I will apply partial fraction expansion, as plus b over s squared plus 1 plus cs plus d s squared plus 4. Okay? And then I will take the inverse Laplace transformation to obtain y of t. If you look at the inverse Laplace transformation of this thing, you're going to see that it is a cosine t plus b sine t, and I would have here c cosine 2t plus d over 2 sine 2t. Okay? And you need to find what a, b, c, d are and then substitute here. Is this function bounded? Is this output bounded? Here you see that sines and cosines here are with constant amplitude. Okay? A is constant with respect to time, b is constant with respect to time, c is constant, and d over 2 is a constant. As a result, the maximum value that such a function can take is just going to be absolute value of a plus absolute value of b plus absolute value of c plus absolute value d over 2. Okay? So I can actually find an upper bound for the absolute value of this function. So this is a bounded output. Okay? So what did we achieve here? So here we started with an Bibo unstable system and show that for some sinusoids, for some bounded inputs, it gives us a bounded output, but there exists a bounded input for which this system would give an unbounded output. Okay? For being Bibo stable, a system should give bounded outputs to all bounded inputs. Here, there exists a bounded input for which the system gives an unbounded output. That is why this system is a Bibo unstable system. But don't think the unstable system just systems which will give unbounded outputs to all bounded inputs. Okay? For some bounded inputs, it can give still bounded outputs, but there exists a very, very specific input for that system which would make the output unbounded. Okay? And for this system, it is this bounded input. All right? So here we see something interesting. So try to repeat this example for any other sinusoid with frequency sine 3t, sine 4t, etc. Okay? So for all of those sinusoids, you would actually see that the output of this system would be bounded. Okay? It is only when the frequency of the sinusoid is equal to 1 or minus 1 when this output gets unbounded. Okay? So this phenomena in control theory has a very, very specific name. It is actually matching the parts of the output, imaginary parts of the output in the input. Here the imaginary part of the poles of this system are 1 and minus 1. And if the frequency of this input matches 1 or minus 1, then the system output would be actually unbounded. This phenomena in control is called the resonance effect. It is related to matching of the imaginary part of the poles on the imaginary axis and the input frequency. Okay? When the input frequency for such a system matches the imaginary part of the poles on the imaginary axis, the output grows indefinitely, although I have a bounded input to this system, right? This is called as the resonance effect in the control literature. So now we have defined what stability is, and now we are going to learn how we can ensure that a system is actually stable, or a feedback system is stable. So let me write the following. In general, the closed loop poles depend on system parameters. And in that case, we would always like to choose these parameters such that the closed loop system is stable. There is a very, very basic example that I use here. So I have a proportional control example, which is given like this. So I am controlling the system, which is given like this: 1 over s, s plus 1, and s plus 2. And this is my proportional controller, and this is my feedback loop. So in this case, when we look at the closed loop system, we will see that the closed loop poles are dependent on the controller parameter. Okay? And then we're going to wonder what type of parameter values, what type of k values would make the closed loop system stable or not. So here our task is find the range of k such that the closed loop system is stable. Okay? So now let me first look at the open loop system. We are, in general, in control problems, we are given the parameters of the open loop system. And the open loop transfer function of this system is this one, is equal to k over s, s plus 1, s plus 2. This is the open loop transfer function of this system. And do you think the open loop system is stable? In the question in the example, we are interested in the closed loop system stability. But here I'm asking you another thing. Is the open loop system stable? This is the open loop transfer function. You need to ask yourselves, what are the poles of the open loop system? I have 3 poles, one at s equals to 0, one at s equals to minus 1, and one at s equals to minus 2. So do you think the open loop system is stable then? The open loop poles are at 0, at minus 1, and at minus 2. Okay? These are the open loop poles. So do you think the open loop system is stable? The answer is going to be no here, because I have a pole exactly on the imaginary axis which doesn't satisfy the stability definition. That means that the open loop system is unstable in the bounded input, bounded output sense here. So there exists a bounded input for the open loop system, and with that bounded input, the open loop system would give you an unbounded output. But the question is related to the closed loop system. Okay? What does it mean? When I close this feedback loop, I obtain another system here. All right? And the system, the closed loop system, is different than the open loop system here. All right? And the question is this overall system from this input to that output, is the closed loop system stable or not? Or which parameter values, K, would make the closed loop system stable? Okay, that is our question. So in order to be able to understand about that, I need to calculate what the closed loop transfer function is. Okay, this is the open loop transfer function. Let us calculate the closed loop transfer function. It is going to be I will use of course the feedback rule here. The forward path transfer function, K over S plus 1, S plus 2, divided by 1 plus. This is a unity feedback system, which means that the feedback path transfer function is 1, and I would have 1 plus everything in the loop. K over S plus 1, S plus 2 here. Okay? So the closed loop transfer function is therefore, if I equate the denominators and cancel here, I would get K over S plus 1, S plus 2 plus K. Okay? And now if I expand the denominator here, K divided by S cubed plus 3S squared plus 2S plus K. So the question is then, for which K values is the closed loop system stable? Sorry. So here, what is the characteristic polynomial of this system? So this is the G closed loop of S. So its poles are determined by the denominator polynomial here. All right? So the characteristic polynomial is d of s equal to s cubed plus 3s squared plus 2s plus k. So we see that we have 3 closed loop poles of this system. We had 3 open loop poles, even like this. They were fixed with respect to the parameter k, but the closed loop poles are the roots of this polynomial, or the solution of these solutions of this equation, this characteristic equation. And I see here that those 3 poles are going to be dependent on this parameter k. Okay? Whatever k value I choose, I would have 3 closed loop poles, and the location of those 3 closed loop poles would change when I change the value of k. Okay? So the question is, for which k values all 3 closed loop poles of this system, all 3 roots of this equation, would be in the open left half plane? Okay? That is our question. And we have a simple method actually in control in order to be able to answer such questions. And that simple method is called the Routh stability criterion, or Routh-Hurwitz stability criterion. It was found at the beginning of 1900s, and to this day control engineers are actually using to answer these type of questions. It is actually related to the coefficient of these polynomials. Based on these coefficients, we form a table, and on that table we apply some operations, and after those operations we obtain a table which would give us our stability criterion or stability requirement on K. So it is going to be our next topic. So let us say that Routh, or sometimes people say Routh-Hurwitz, these are the mathematician names who found this criterion, stability criterion. Okay? And now we are going to learn about this simple criterion. Unfortunately, the Routh stability criterion is a very complicated algebraic result. So in order to be able to prove that, we have to know really lots of theorems or proofs from the field of algebra. Okay? And it is a very deep field in mathematical studies, and engineers usually do not have the mathematical tools in order to be able to prove such results. Okay? So here we won't see how this result is obtained, but we are going to see how we can actually apply this result in order to be able to get our stability conclusions. All right? So I won't teach you, unfortunately, why this happens. So I will just teach you how you can apply this. I won't give you the answer of why, but I will give you the answer of how. So we're going to start with an arbitrary characteristic polynomial, which is going to be looking like this. A0 s to the n plus a1 s to the n minus 1 going until an minus 1s plus an. And here I have only a single assumption, and that is a0 is strictly larger than 0. Okay? So do you think this is a loss of generality? Assuming that a0 is positive, do you think it is a loss of generality? Am I losing my ability to apply this criterion on some polynomials? So remember, our result is going to be related to the roots of this d of s. Okay? If I have a d of s with a negative coefficient here, then I can multiply that d of s with minus 1 without changing the root locations. Okay? Instead of a positive a0, if I had a negative a0, what I can do is that I can multiply that d of s with minus 1, and that wouldn't change my pole locations, because the roots of a polynomial does not change when we multiply that polynomial with minus 1. Okay? So if instead of a positive a0, if I had a negative a0, what I can simply do is that multiply that polynomial with minus 1 and apply the criterion on that new polynomial. Okay? That would give exactly the same result, because I don't change the pole locations at all by multiplying that polynomial with minus 1. So this is not actually a loss of generality here. We are still general if you remember that when we have a polynomial starting with a negative coefficient, we need to just remember to multiply that polynomial with minus 1 and continue as usual. So now let us look at what is usual here. So we construct the following array. This is called Routh's array. Okay? So in order to construct the array, I will write here some powers of s to the n, s to the n minus 1, s to the n minus 2, s to the n minus 3. So we're going to reduce these powers until s and 1 here. Okay? We know that 1 is nothing but s to the power 0. So we are going to be writing all of the powers of s, starting from the highest power in the polynomial, going until the lowest power that we can have, s to the 0. And then here is what I'm going to do. Into the first row of this array, I'm going to write the first coefficient a0, and then I will skip one of the coefficients and I will write a2, and then I will skip again one of the coefficients and I will write a4, skip one and write a6, a8, etc. Okay? I have written all even numbered coefficients here into the first row. All right? Now let us write the remaining coefficients into the second row. So I will take a1 here. This is s to the n minus 1. So you see that here the first row was related to s to the n. So I started with a0 here, which is the coefficient of s to the n. and then I skipped one coefficient and I have written A2, A4, etc. And the second row is related to S to the n minus 1. I will first write the coefficient of S to the n minus 1 here, which is A1, and then I will skip one coefficient and I will write here A3, A5, A7, etc. Okay? So these are the first two rows of the Routh array. And now I'm going to fill in the remaining rows. And the remaining rows are filled as follows. So if I want to fill in this element here, let me say that it is B1. B1 is formed out of these four elements on top of it. Okay? And the formula for B1 is going to be the following. B1 is equal to, I will multiply this A1 and A2, and then I will subtract A0 times A3, and I will divide the result by A1. So this is going to be A1, A2 minus A0, A3 divided by A1. Again, here I'm not teaching you why I am doing this. Okay? Why do we do such a calculation? I won't be able to explain this to you. Okay? It is a very, very deep mathematical result in the mathematical field of algebra. Okay? So we don't know actually, of course the mathematicians know, but as engineers we don't know why this happens, or why we need to do such a calculation. We just know how to do this calculation, and then we know how to interpret the result. So this is my B1, and it was obtained by using these four coefficients here. So let us calculate B2. B2 is now going to be calculated not with these four, but these two. These four. Okay? And here is what I'm going to do. I will multiply A1 and A4 minus A0, A5 divided by A1 again. B2 is A1, A4 minus A0, A5 divided by A1. So I would always be dividing by A1 here, this coefficient on the one row above. Okay, the first coefficient on the row above here. And let me write B3. Now B3 is going to be calculated by using these four numbers. Okay? And B3 is going to be the following. A1 times A6 minus A0 times A7 divided by A1. Okay? And this finishes the third row. All right? So here, this calculation, if you get a matrix, a 2 by 2 matrix with these elements here, you know how to calculate the determinant. Here, we are always calculating the negative determinant, okay? Determinant would be A0, A3 minus A1, A2. So here we are calculating the negative of that, A1, A2 minus A0, A3. Okay? This is a negative determinant of that 2 by 2 matrix. So you can remember it as the negative determinant of those four elements, either this, or this, and divided by the first coefficient of the one row above. All right? So now let us go one row below here. So I can write here C1. Now in this case, C1 is going to be calculated by these four elements. All right? So let us calculate that. C1 is, remember the negative determinant here, B1 A3 minus A1 B2 divided by B1. Okay? Let us go into C2, and then I will use these four elements. All right? And C2 is going to be, I would have B1A5 minus A1B3 divided by the B1. Okay? So we are going to continue in this manner. If I go one row below, I'm going to have D1, and D1 is going to be calculated by these 4 elements, and D1 is going to be C1B2 minus B1C2 divided by C1. Okay? So we are going to continue, and as we continue like this, we are going to see that the number of elements that we need to calculate will get fewer and fewer, will get less and less. Okay? And at the last row, we're going to have a single value, which is going to be E1. Okay? And this type of computation is going to calculate the so-called Routh array. All right? And after we calculate the Routh array, we are going to concentrate on its first column. Okay? Only its first column is going to be important for us. First column of the Routh array. Okay? And our conclusions are going to depend on the signs of the numbers in this first column. Okay? So let me write here the results that we can get from the Routh array. The first result is said that the system with characteristic polynomial d of s is stable if and only if. I sometimes write this IFF instead of if and only if. So this means if and only if the first column of the Routh array is all positive. Okay? If all of the elements of this first column of the Routh array, if they are positive, then the system is stable. The system with this characteristic polynomial is stable. If not, the system is not stable. Okay? This if and only if means just that. Okay? If we have a first column which is composed of all positive elements, then the system with the characteristic polynomial d of s is positive. If not, then the system the system with this characteristic polynomial d of s is stable, and if not, the system is not stable. All right? The second result that we can get from the Routh array is the following. So I will erase this part. The second result that we can get from the Routh array is given as follows. The number of poles, the number of roots of d of s, these are the poles with positive real parts. Is equal to the number of, this is the number of roots of d of s with positive real part is equal to the number of sign changes in the first column of the Routh array. Okay? So there are two results here. The first thing is related to the stability. So we know that the system is stable if the first column is all composed of positive elements, and if the system is not stable if there exist negative or zero elements in the first column. And the second result is related to the number of roots of d of s. So number of poles of this system with positive real parts, okay, is equal to the number of sign changes in the first column. Okay? So if I look at the first column here of the Routh array, suppose that the numbers are 5, 6, minus 7, 3, 5, and 2. Let us say this is my first column at the end of this calculation. Then what is the number of sign changes here? The number of sign change, this is a positive number, positive, so no sign change here. There is a sign change here, which is from positive to negative. The system is obviously not stable because the first column is not all positive. But I can still extract this information from this first column. And the number of sign changes here, from minus to plus here, is 1. And there are no sign changes here. Let me say that this is minus 2. In that case, I would have one more sign change here. So in total, in this first column, hypothetical first column, I would have 3 sign changes. And that would mean that the number of roots of this polynomial that I obtained my Routh array with positive real parts is equal to 3. Okay? So in general, we try to obtain both of the results from the Routh array. Okay, once we form it. So here, what is the condition for these roots? So we are here, the number of roots with positive real parts means that the poles in the open right half plane. Okay, these are meaning that poles in the open right half plane. So positive real parts means that real of S is strictly positive. Okay? So this number, the number of sign changes, does not give you the number of poles on the imaginary axis or the number of poles in the open left half plane. Okay? It only gives you the number of poles in the open right half plane with positive real parts. So now we have actually obtained this result, and now I'm going to apply this Routh array idea on the problem that we started with. Okay? You remember the problem? It was this characteristic polynomial. Remember, for this system, we asked when the closed loop system, for which k values is the closed loop system stable. Okay? And the characteristic polynomial of the closed loop transfer function would be just this one. All right? And now we're wondering for which k values is the closed loop system stable. So in order to be able to do that, so let us write back to the example. I will form my Routh array and I will calculate this first column depending on k, and then I will try to make all of the elements in the first column positive for stability. Okay? So I'm trying with this d of s. The first coefficient is 1, which is positive, so I can apply the Routh stability criterion directly without multiplying with -1. So I have here s cubed, s squared, s, and I have 1. So s cubed, s squared, s to the 1, and s to the 0. All right? So now let us start with s cubed coefficient here, which is 1. I will skip one coefficient and I will go to this one, which is going to be 2. And s squared coefficient is 3. And the next coefficient is just k. So we see that after some point you ran out of coefficients here, so you stop there. But you can think that you have just zeros here if you need these numbers. You can just assume that these are both equal to 0. So you generally stop when you run out of coefficients, but you can, if you need these numbers at some time during your calculations, you can assume that they are equal to 0. Okay? So now let us try to calculate. So these are the first two columns. Let us calculate the third column. So it is 6 minus k divided by this number. which is 3. Okay? So am I going to write anything here? So if I want to write anything here, then I would use these two numbers with these two numbers. Okay? But these two numbers are already 0, so the multiplications would be equal to 0. Divided by 3 would be equal to 0. So I would just put a 0 here. So in general, I really do not feel the need to write zeros here, so I stop just here. Okay? So, but you can just write 0 here. And let us write the next row here. I'm going to write this number. It's going to be multiply this one with this one. So multiply these two minus multiplication of these two divided by this one. Okay? So we see that since this coefficient is equal to 0 here, I will only multiply these two and divide the result by this one. Okay? Multiply these two minus 0 divided by this one, it's going to be k. Okay? So when you have a triple with a 0 here, when you have a triple, these three numbers and 0 here, the result is usually just this one. Okay? Is going to be just this coefficient, and it is just equal to k. So this completes my Routh array, and now I need to concentrate on the first column of it. Okay? So this is my first column. Okay? So now we are wondering about the k values for which the closed-loop system is stable. So if the system is stable, we know that the Routh array first column is going to be all positive, and if the Routh array first column is all positive, the system is going to be stable. So that is why we're going to make sure that for stability, we need all of these k-dependent terms positive numbers. These 1 and 3 are already positive, and if I have these two numbers, positive numbers, the system is going to be stable. So I will set 6 minus k is going to be positive, and I have k is going to be positive. The first inequality is going to give me k smaller than 6, and the second inequality is already k larger than 6, which means that the stability range for k is the interval between 0 and 6. And it's an open interval. The boundaries are not included. Why? Because if k is equal to 6, this element is going to be equal to 0. So I will lose the property of first column of Routh array being positive. Okay? 0 is not a positive number. Okay? And if this inequality is satisfied with equality, I would have the last element equal to 0. In that case, the first column would not be positive. That means that for stability, I cannot include any equality here in these inequalities. Okay? So this is our stability range. So I will solve one more example. Consider a system with transfer function g of s is equal to n of s over d of s, where d of s is given as follows: s to the 4 plus 2s cubed plus 3s squared plus 4s plus 5. Right? Now we're going to investigate the stability of this system using the Routh stability criterion. Investigate the stability using Routh stability criterion. So so I will apply the Routh stability criterion on that characteristic polynomial here. So I have s to the 4, s cubed, s squared, s, and 1 here. So let me write the coefficients. The first coefficient is positive, no need to multiply with -1. So I would have 1, skip 1 coefficient, so it is going to be 3, and skip 1 coefficient, it's going to be 5. And the coefficient of s cubed is 2, skip 1 coefficient, and 4 here, and 0. So when you run out of coefficients, you can just put 0 here. And let us calculate the rest. So it is 6 minus 4, which 2 divided by 2 is 1. Okay? And 2 times 5, 10, minus 0, it is still 10, divided by 2, it is 5. So you see here again the same pattern. So triple numbers and 0 here, it gives you this number, 5. And you can put here 0 or not, it really doesn't matter. So then I have 4 minus 10 is minus 6, divided by 1 is minus 6. And here, you see 0 here, and I have another 0 you can think, and it's going to be just 0 here. Okay? You can write it, or again, you might not. It really doesn't matter. And this is again a triple, and 0 here, which is going to be 5. So this completes the Routh array. And do you think such a system would be stable or not? The answer is clearly no, because the first column of the Routh array is not positive. That means that our system is not stable. But here, the interesting thing is that when the system is not stable, we can still learn about the number of roots of d of s, this polynomial, with positive real parts by counting the sign changes in that first column. Okay? So this is still an extra information, and even if the system is unstable, we usually want to continue with the Routh array. So here, for example, as soon as I obtain here -6, if I am interested in only the stability of the system, I really do not have to continue. Okay, but we usually try to continue with finishing the Routh array so that we can learn about this number. About the polynomial. Okay? Here I need to count the number of sign changes. No sign changes here. There is here a sign change, which is going to bring me +1, and there is another sign change here from minus to plus. So I would have 2. So I have 2 poles in the open right half plane. Okay? 2 poles with real of s positive. Okay? It really doesn't tell us anything about the remaining poles. The remaining poles can be on the imaginary axis, or they can be in the open left half plane. So the Routh array only gives us information about the poles in the open right half plane. Okay? So how many total poles do we have here with this characteristic polynomial? How many poles do we have? In that case, that is a 4th order polynomial, and it means that we have 4 poles in total, and 2 of them are in the open right half plane. So meaning that there are 2 poles here in the open right half plane, either in this form or in this form. Okay? Here I actually know the roots of this polynomial, and I know that they are going to be in this form. Okay? But where are the other 2 roots? Does Routh array tell you anything about that? No, the other two poles can be here on the imaginary axis, or they can be here in the open left half plane, or they can be on the real axis on the left half plane, etc. Okay, so you won't know where they are. The only thing that the Routh criterion, Routh array, is telling you that by the number of sign changes here is the number of poles in the open right half plane. You don't get any information about where the other poles are. Except that you know that they are not in the open right half plane. They are somewhere either on the imaginary axis or in the open left alt plane. Okay? So this completes this example, and I have the final example here. In this case, I won't write the question, I will just write d of s. I have s cubed minus 3s plus 2, which is the characteristic polynomial of a system. And I would like to understand whether this system is stable or not. And if it is not stable, I would like to know the number of poles in the open right alt plane based on the Routh stability criterion. Okay? So now let us form the Routh array. S cubed, S squared, S, and 1. So I will write the coefficients here. S cubed coefficient is 1. No need to multiply with minus 1. So 1. Skip 1. So you need to think that there is a 0 S squared here. Okay? So you shouldn't just jump to the next coefficient here. You need to think that this polynomial is S cubed plus 0s squared minus 3s plus 2. Okay? So here you need to skip one coefficient. You shouldn't skip here minus 3 and go into just 2. The next coefficient here is 0. You need to skip that and you need to write minus 3 here. Okay? And the next thing that you have to do is to write the coefficient of s squared, which is equal to 0. And skip 1, minus 3, and I write 2. All right? So now I would like to continue forming the Routh array. But I want to just to look at the first column now. Now, as soon as you write these coefficients into the Routh array, you see that there is a 0 in the first column. Okay? What does that mean? That means that the first column of the Routh array really cannot be positive anymore. I got a 0 there. 0 is not a positive number. That means that whatever I do afterwards here, the first column will never be positive. So as soon as you see that 0 there, you can actually conclude that the system is unstable. Okay? There are not all poles of this system, not all roots of that d of s can be in the open left alt plane. Okay? As soon as we see 0 in the first column, we conclude that system is not stable. Okay? But as I told you, even when we think that the system is not stable, we would still like to continue by forming the rest of the Routh array. Okay? So here, let us try to form the rest of the Routh array. So I will write 0 times minus 3. It is going to be 0 minus 2 divided by this element, 0. So what is this going to be? So you see that in this Routh array calculation, there is a weak point. Okay? And this weak point is that when you encounter a 0 in the first column, then really you get a 0 division here. You get a division by 0 in the next row. Okay? So this actually makes you unable to continue to form the rest of the Routh array. Okay? So this is called a difficulty that you can encounter in forming the full Routh array. Okay? So this is just one of the difficulties. A difficulty this is called the first difficulty, and it is the first column of it is one element of first column being equal to 0, while there are non-zero elements in the same same row here. This is called the first difficulty, and there is actually a second difficulty which is quite similar, and that is going to be one of the rows of the Routh array being completely equal to 0. Here, this is not just completely 0, so you have just the first difficulty, but sometimes you have double zeros here, which makes the full row equal to 0, and that is called the second difficulty. Okay? So this is, I will put here a question mark. We are actually going to be learning about what to do in these type of cases. But here, you need to still remember that as soon as you encounter a difficulty in forming the Routh array, that means that your first column is no longer is positive. Okay? That means that the system is unstable. And why are we continuing still, or why are we still trying to form the rest? In order to be able to get the second result from the Routh array. Okay? In order to be able to learn about the poles of this system in the open right half plane. All right? When you get a 0 in the first column of the Routh array, this is called a difficulty. There are two difficulties. Difficulty 1 is a row of this form, 0, let us say 0, 2, 5, etc. Getting a row of this form. The element in the first column is equal to 0, but there are some non-zero elements in the other elements of the row. This is difficulty 1. Difficulty 2 is getting a 0 in all elements of the row. Okay? This is called the second difficulty, and it is actually easier to solve such a difficulty. So here, there are some multitude of solutions in order to be able to continue forming the Routh array here. One of the solutions is just to replace this 0 with an epsilon. Okay? And replacing this with an epsilon, we can continue forming the rest of the elements, and then we can count the number of sign changes at the end of this calculation. There are also solutions for the second difficulty, and usually the second difficulty is a good thing, and it gives us really a lot of information about the roots of this D of S. But I'm not really going to go into those difficulties, because with these topics we have actually come to exactly the middle of EE381, and you are going to be taught about these topics by the other professor of this course, Professor Kemal Leblebicioğlu, and I will actually stop giving the lectures to you now, and I will just actually try to come back if there is a need at the end of the course. So here, I won't actually continue with this, but I would like to just mention about what about topics are awaiting you in this course. I would just like to mention about those topics. So the next things that you're going to learn are going to be this difficulty 1 and difficulty 2 in forming the Routh array. So they are not going to determine the stability, but they're going to allow you to be able to continue with the formation of the Routh array. And the next topic afterwards is going to be called root locus. Okay? And it is going to be actually the most important topic of this course, and probably the most informative part of this course. So here, let us go back to this system. This system is a control system which is dependent on a single parameter k, and I have calculated the characteristic polynomial of this system, and it was s cubed plus 3s squared plus 2s plus k. Okay? So, and what did we do with the Routh array? With the Routh array, we determined the stability range. Okay? So, if k is between 0 and 6, then the system is stable. Otherwise, the system is not stable. But we see that the Routh stability criterion does not tell us anything about the system performance. Okay? It can only tell us an information, stable or not stable. Okay? It is only this piece of information that we get from the Routh stability criterion. In general, we would really like to know when the system is stable, what would be its transient performance, etc. So when the system is stable, does it have a good settling time? Or does it have a good overshoot property, etc.? We would like to learn about this. So in order to be able to do that, we use the concept of root locus. All right? What does root locus do? Root locus tries to draw the closed loop poles of the system as k changes between 0 and infinity. Okay? We change k between 0 and infinity. We know that the system is going to be stable only in between 0 and 6, but we are going to be drawing the closed loop pole locations when k changes between 0 and infinity. Okay? And based on that plot, we get really a lot of information about the transient performance of the system as well. All right? So, how does a root locus look like? So a root locus is a plot of the roots of this polynomial as k changes between 0 and infinity. There are 3 roots, 3 closed loop poles, and they change their places as k changes between 0 and infinity. Okay? So the first question that we ask is, where are the roots when k is equal to 0? At the beginning of root locus, where are the closed loop poles at k equals to 0? So just substitute k equals to 0 here, and you get s cubed plus 3s squared plus 2s plus 0 equals to 0. And this 0 is ineffective here. So what are the roots of this polynomial? Take s parentheses, s squared plus 3s plus 2 is equal to 0. This tells me that s equals to 0. So this is s plus 1 times s plus 2. S equals to minus 1 and s equals to minus 2. Okay? So when k is equal to 0, these are my closed loop poles. This is the characteristic polynomial. And my closed loop poles are at s equals to 0, minus 1, and minus 2. This is where root locus starts. Okay? Minus 1, minus 2, and 0. But these are the open loop poles of the system. Okay? So you see that this is nothing but s cubed plus 3s squared plus 2s. Okay? The roots of this are, so root locus always starts at open loop poles. 0, minus 1, minus 2. Then you're going to learn some principles here. These principles will show you how these poles are going to move in the S-plane as k changes between 0 and infinity. You will see, for example, that for this example, you will see that if I increase k just a little bit above 0, these 2 poles are going to approach each other. There will be always 3 poles, and these 2 poles will come here, and this pole is going to go here. Okay? You won't understand now why this is happening. Okay? You will be able to understand it in the concept of root locus. So what happens as I increase k? You will see that these poles will approach each other. 2 poles will come here, and there will be a 3rd pole here. And then these poles, as I increase k, these 2 poles will approach further to each other, and this pole is going to still move to the left. Okay? And there is going to be coming a significant k value at which we are going to have exactly 2 poles at the same location. And this pole would still be going to the left. Okay? So if I increase k above that critical value, what is going to happen is that these two poles, exactly at the same location, will go into the complex domain. So one is going to come here, the other one is going to come here, and this one is going to go there. So there will always be three closed loop poles, but you're going to draw their trajectory as k changes between 0 and infinity. We started at these three locations at k equals to 0, and then these two approach each other as k increased, and this one went there. But there are always three poles for each single k value. Okay? And if I continue increasing k, these two poles are going to come here, and this is going to continue going towards there. And if I combine these trajectories, so at each k value there are three poles, but if I continuously combine these trajectories, we're going to be drawing a trajectory which is looking like this. So I will have this part here. There is a pole going in that direction as k is increasing. There is a closed loop pole going in that direction. And there are two poles going in this direction, approaching each other. And then they're going into complex domain, and they would be diverging towards infinity. You would see why this is actually happening. Okay? And you see that from such a picture, you will be able to tell really a lot of things about the system performance. First of all, I told you that the system is stable when k is between 0 and 6. If k is different, k is outside this range, then the system is going to be unstable. So what is the k value at which the closed loop poles intersect this imaginary axis, if I ask you? So we see that for small k values between 0 and some value, all of the three closed loop poles are in the open left half plane. Okay? When all three poles are in the open left half plane, the system is stable. When do we have the fact that the system now has not all poles in the open left half plane at this intersection here? So this intersection is actually the point when k is equal to 6. Okay? And if k is larger, if k is equal to 6, there will be two poles on the imaginary axis and one pole somewhere here. And if I increase k above 6, there will be two poles in the open right half plane. You can actually see these using the Routh stability criterion, and there will be another pole somewhere here. But the system would be unstable in that case. So by looking at such a picture, you will be able to say really a lot of things about the transient performance. So here you really do not have to understand the details here. You will see these topics in more detail, and they're going to be taught by Professor Kemal Leplevicioğlu. But here I will just mention mention one thing here to you, and it is going to be the following. When is the settling time of this system is minimum? When is the settling time at a minimum for this system? I will just ask you this question. So the settling time is determined by the distance of the closest pole to the imaginary axis to the imaginary axis. Okay? So settling time of a system is determined by the distance of the closest pole to the imaginary axis to the imaginary axis. Okay? So here, where is the closest pole to the imaginary axis is furthest away from the imaginary axis. So when I look at this picture, there are two poles coming here as k is increased, and this is going to the left. So these are the dominant poles here. Okay? These two poles here are the dominant poles, and as I increase k, the closest pole to the imaginary axis, this one, is getting further away from the imaginary axis. Okay? As I increase k from 0, the closest pole to the imaginary axis is getting further away from the imaginary axis. Okay? And at some point, these poles goes to the complex domain, and they start approaching to the imaginary axis again. Okay? So this point where this intersection happens is going to be where the system has the smallest settling time. Okay? Because it is the point at which the closest pole to the imaginary axis is furthest away from the imaginary axis. Okay? You will see these in more detail in your future lectures. So this root locus, you're going to spend 2 or 3 weeks in the semester. And the final topic of the course is going to be called the state space analysis. State space. And in that case, you're going to see the following. So instead of a transfer function like this here, you're going to have a state space representation as your system model. Okay? Y is equal to Cx plus du. So this is u, this is y. In all of EE381, you will see control systems like this, except this last part, which is related to the state space. Okay? So in the earlier part, what we saw in the feedback was that we measured the output and then we fed it back to the input. Okay? In all of the earlier parts, we have seen the measurement of the output and feeding it back to the input. When you have a state space model for your system, instead of feeding the output only back to the input, you can actually try to measure the state x, which is a vector from the system, and you can try to feed it back into the output by multiplying it with a gain parameter k. This is going to be a horizontal vector, and this is going to be a vertical vector, and when these two are going to be multiplied, they're going to give you a scalar to feed back to the input. And this is called the state feedback, which is a very powerful feedback strategy, which is only valid for systems with state space models. So at the end of the course, you're going to go into the state space models, and you will see the advantage of the state space models by applying state feedback instead of only output feedback, as in this figure. Okay? And that is going to complete the course. So I would like to thank you a lot, really, for watching the videos. I actually followed the number of watches from the YouTube, and I've seen that really a lot of you has watched my videos. I'm very glad that you are not bored with them, at least. So there is going to be a change now in the teaching style of the course. So unfortunately, I can do nothing about it. But you have to be sure, you have to remember only one thing. So there is nothing really beyond your abilities in this course. Sometimes students of this course would be really afraid by the mathematics, but as you have seen until this far in this course, there is really nothing beyond your abilities. So if you continue studying, if you continue to follow the material, if you continue to ask questions, then you're going to succeed. So please do not be discouraged. Thank you very much. Bye-bye.